I am very thankful for the high auditorium for giving me a possibility to make this invited lecture, which is a great honor to me to share some of our results with all of you. So, my talk will be devoted to the topology of simply connected fractal squares. Really, these results can be applied not only to fractal squares, but also to Bedford-McMullen carpets and Baranski carpets. But it's more easy to show all these things on squares and then extend it to other matters. What is a fractal square? So, fractal square is very simple kind of fractals. It is constructing the following way. We take a square, say n multiplied by n. Yes? We take union square and divide it into n squared smaller parts. Yes? Then, after that, we choose some of these smaller squares and look at the lower left corner points of these squares. So, coordinates of these corner points will be di divided by n, where di are the part of a set D, and D is 0 n minus 1 squared. You see, each coordinate is KL, where KL divided by n, where K lies between 1 and n minus 1, and L lies also some integer number between 1 and n minus 1. Yes. And we construct a system of similarities, sending this large square to these distinguished squares, to these chosen squares. Yes? So we write K is equal to union of SI of K, but SI of K is a multiplication by 1/n and translation to the number di. Therefore, we can write it in more compact form. D plus K divided by n. Right? So, this is the definition of a fractal square. Very simple. So I need not remind to you the definition of a self-similar set because I repeated it several times. So this definition of fractal square is the following. So we have the set of digit set D, which is a subset of 0, 1, and minus 1 squared. Yes, and a fractal square is the set which satisfies the equation K equals to K plus D divided by n. The immediate consequence of this equation, which explains why we call these points digits, is that each element of this fractal square can be written in the form sigma, the sum of dn divided by, dk divided by n to the power of k. So the points of a fractal squares can be represented as infinite fractions. But the digits in these fractions are not 0, 1, 2, 3, 4, 5, 9, but the digits in these fractions are just these chosen points. So this is a fractal square. Very interesting and simple. So this is a typical fractal square, 5 by 5. So I have a square 5 by 1 by 1. I divide it into 25 parts, and I have chosen these parts. And after constructing the system of similarities, I get this fractal square. It is obvious that if this square if these copies, the intersection graph of the system of these copies is connected, then fractal square is a continuum. Yes, but the problem of how it is connected is very interesting, because each square has 1, 2, 3, 4, 5, 6, 7, 8 not neighbors. Because squares can have side neighbors and they can have vertex neighbors. And if a vertex belongs to fractal square, if a pair of opposite vertices belong to fractal square, then these two copies will have non-empty intersection. They will intersect in one point. From the other side, if two squares have common points on opposite sides, then the intersection will also be non-empty. Yes. Oh, this is a faculty coming. So a fractal square is a special case of so-called fractal cubes, and fractal cubes can be made in all kinds of dimensions, and there are two. One example of a fractal cube is very familiar to you. It's a Menger sponge. Yes, it is made of 20 cubes, smaller cubes, and this is some kind of variation of Menger sponge, because it consists of two groups of cubes. One is inside the other and they do not touch. Yes, therefore this fractal cube has uncountable number of connected components, uncountable family of connected components, and they are all, tied together. So we have a kind of Menger sponge which is outside, we have a kind of cross, and we have also a great number of components which are in between them. And they form such a nested family of components. So the problem of connectedness of self-similar set is related to so-called self-similar boundary. So if you have a self-similar set, for example this one, you have a self-similar set, its copies intersect each other. Yes. So these intersections of copies form so-called critical set. Yes. But if we consider maybe a more complicated example, like this, we'll find very interesting property that this intersection points, if we take the pre-images, they give some other points. And if take the pre-images, we get other points. And the set of all pre-images of intersection points form the set of addresses of pre-images of intersection points form so-called post-critical set. If this post-critical set is finite, then we call the self-similar set post-critically finite. For example, Sierpinski gasket has these three critical points, and their pre-images are this, and these 3 points are called the self-similar boundary of a self-similar set. Because all copies of self-similar set intersect by the images of the points from boundary. So everything which all aspects of relations between different copies of a self-similar set are expressed in terms of the points of self-similar boundary. If the self-similar boundary is empty, then the set is totally disconnected, yes? If a self-similar boundary consists of 3 points, the set is very simple. But of course we can construct a self-similar set which is a dendrite and which has infinite self-similar boundary. How to do this? We just need to choose proper points, because each point has a sequence of its predecessors. Yes? So a point has address I1, I2, I3, I4, etc. X is image of this sequence. And if I take this address, then Y is P of I2, I3, etc. Then X is equal as I1 of Y, right? So Y is the predecessor of X. And then if we begin to shift along this sequence further and further, we'll get this infinite sequence of predecessors. But in some cases, these predecessors are always the same. For example, this point has 2 predecessors, this one and this one. And these points are predecessors of themselves, yes, because these are periodic points. So this point is an image of this point and this too. So the critical set is the set of points of pairwise intersection, and the set of all the predecessors of critical points form a self-similar boundary. And our interest is to understand how the self-similar boundary of a fractal square looks. As I already explained to you, if we have a self-similar set and its copies have non-empty intersection, then we can form an intersection graph. If this graph is connected, then the set is connected. But when we consider this intersection graph, these intersections may be very large. The other thing happens when the system has one point intersection property. Then the intersection graph will look something like that. In this graph, we consider the points, intersection points, as the vertex of second kind, and we have more detailed intersection graph. So the tractor K over system S is connected if the intersection graph is connected. And if a continuum possesses one point intersection property, like in the case of Sierpinski graphic cascade, then we can make a more detailed intersection graph with vertices of two kinds. Vertices of one kind are the copies, and the vertices of second kind are the intersection point. So if we have a self-similar set whose intersection graph is a tree, and it possesses one point intersection property, then the attractor is a dendrite, and we built such dendrites. We already created such ones. So this theorem was proved quite long ago. Yes, first it appeared in the paper of Band as one line. If this system has such graph as a tree, then the attractor is a dendrite, without any explanations. But of course, it had to be considered in more detail. Now you see a fractal square. You see? Yes. And its attractor, it's a system, this is a system of squares, and this is the attractor, and this is the intersection graph of this system. Please look. What can you say about this intersection graph? It is a tree. It has no cycles. Therefore, this picture is a dendrite. It's a dendrite because it cannot have any closed loops inside. Of course, if the intersection graph of a self-similar square is a tree, then the attractor is a dendrite. But is it true to the other side? Because we can consider dendrites whose copies intersect in a line. Or, as I showed you in previous example, we can construct a dendrite whose copies intersect in some complicated topological tree or even a subdendrite. But this cannot happen for fractal squares, because if a fractal square has, if the intersection of two copies of a fractal square is simply connected, and it is not a point, it can contain an interval. But if it contains an interval, and this interval is also consists of smaller copies, but to have an intersection of two copies in one interval, we need to have one interval on one side and the other interval will be on the other side. But if we have the intervals on two sides, then this picture will repeat in smaller copy, which will lead us to appearance of loops, of closed curves, so it cannot be a dendrite. Therefore, we have very interesting theorem. if a fractal square is simply connected, then either it is a square, completely filled square, or it is a dendrite. There are nothing between these two possibilities. There are no intermediate possibilities. This statement is true not only for fractal squares, but also it is true for Bedford-McMullen carpets. And even some topological carpets are more complicated structure. So what happens with the components of a fractal square? So if you have a fractal square, then it has 4 sides. These sides may be empty, may be non-empty, but each side is an intersection of fractal square with this interval. And it is a fractal square itself because it is generated by those chosen squares which intersect this side. Therefore, each side of a fractal square is a fractal segment. So it is some kind of counter set. We take a segment, divide it into n part, choose some of these parts, and the attractor of this system will give us a fractal segment. The problem is, suppose we have 2 fractal segments, then the intersection can be written in this form. And so maybe I will skip these details. It depends if you have 2 fractal segments. Yes, I will write one segment and the other segment. Right, one segment will be marked by red lines, maybe this one, and the other segment will be marked by green lines. Say this, and this. Yes. So some of these parts will be common, yes, and some of these parts can intersect in n points. Yes. So if you have more than one common part, then the intersection will be a counter set. It will be uncountable. So if the number of common parts over 2 fractal segments is more than 1, then the intersection is uncountable, and we don't need it because we need one-point intersection property. The second problem is if we have only one common point or only one common copy. In that case, there will be a fixed point, and the intersection may be countable, or it may be 1 point, or it can be countable. If when it is countable, for example, consider this the case when say we have these copies and these copies, right? If red fractal segment contains this copy, then it contains this point. If a green fractal segment contains this copy, it contains this point. Therefore, this point will be common point of these 2 segments, right? And it will repeat countable number of times. It will repeat countable number of times. Therefore, the intersection of two fractal segments contains one or less parts, then the intersection may be countable, but in some good cases it consists of only one point, and we are interested to have only one point intersection. And these common points of the intervals give rise to common points between copy. For example, if we have two squares here, yes, then if two copies meet on such site, then this point comes here, this point comes here, and that's all. What I have to do? Exit? No. Oh. Can I erase this insect? Yes. Yes. And for example, if we have two copies which have common vertical side, then they will meet in this common point. So if on each pair of sides we have only one pair of common points, then everything is okay. Our set will have one point intersection. So in that case, if we have a fractal square like this, you see it has these two sides have three intersections. So there will be any two, if we take this fractal segment and take this fractal segment, they will have one and one and 2 points. And you see that on each vertical side, when they are neighbors on a vertical side, we have 2-point intersection between this copy. It is good just for us to know that such possibility exists, but to consider the simply connected case, this can be ruled out. This possibility needs to be ruled out. Yes. So, summing up all the problems, we see that if we have a simply connected fractal square, which is not a line segment, then it can have 4 types of boundaries. 4 types of boundary. First type of boundary, then we have 2 common points on opposite side, opposite vertical sides, and 2 common points on opposite horizontal sides. Yes, second case, it's a boundary of a type 2 when we have 2 common points on vertical or horizontal side and have 2 common points on opposite diagonal points. Yes. Third one, if a fractal square is simply connected, then it can have boundary, so similar boundary of this type when we have 2 pairs of opposite diagonal points. And finally, it is possible that we have opposite diagonal points, opposite vertical points on vertical sides and opposite points on some of diagonal. It will be type D. So the four boundary types A, B, C, and D. But D can be quite simpler. We can have this point, and this point. These 2 points are opposite points on horizontal sides. These 2 points are opposite points on vertical sides, and these are diagonal points. So they're type D3 and D4. For example, this is a fractal square of the type A, because we have 2 opposite points here and we have 2 opposite points there. So they intersect, the copies intersect on horizontal sides or on vertical sides. And this is a type B because the neighboring points lies on diagonals. So all this fractal square looks this way. And it is impossible if n is even number. Only n must be odd. For example, this fractal square has the order 1, 2, 3, 4, 5, 6, 7. Yes, it's 7. It is a square of 7 by 7. And this is a type C. Type C. We have a vertical and diagonal. Type C is, I forgot to mention it. So it is possible when we have 2 neighbors on a diagonal and 2 neighbors on opposite vertical or horizontal sides. It's a type C because we have this vertical neighboring and we have diagonal neighboring. But how do you think? Is it a dendrite or not? Do you see any cycle here? No, there is no cycle because intersection graph is this, and this. Yes, intersection graph is a tree. Therefore, this fractal square is dendrite. And this is a fractal square of the type D3. When 2 squares can intersect on a vertical line, 2 squares can intersect on a horizontal line, and also they can intersect on a diagonal. But only on one diagonal, because it is impossible to make more than one diagonal in that case. And this is D6 when vertical neighboring points are these 2. Yes, horizontal neighboring points are diagonal neighboring points. Horizontal neighboring points are these, and diagonal neighboring points is here. Yes. So it is type D6. So if you have a fractal square dendrite, then for any point, the order of this point cannot exceed 4. Because why it is so? If we take a fractal square and sum of its neighbors, if we have 5 neighbors, then we'll have a cycle. Because an order of the point is the number of neighboring component to a fractal, to a copy which consists. So there are several relations between copies which finally lead us to the following result. So fractal square dendrites may be divided into 7 types depending on the form of their main tree. So the main tree may be this way, it may be this way, this way, this way, and this way. If I had the time, I could explain it in more detail, but now we need to finish. So these are fractal squares of the first type, when the main tree is a Jordan arc. You see, this is a fractal square, this is a main tree. It's simply connected. Oh no, so it is just an arc. The second type, when the main tree has this form. You see? So one point, this common point, may be on the boundary and even on the self-cylinder boundary, but there are 4 possible types of fractal square with such a main tree. Then we can have the third class. You see it? When main tree is diagonal cross. It can be of type A. Yes, it may be of type B, and it may be also of type C. And main tree can be this type. It can have 4 vertices, and 2 vertices are of the order 3. So these are examples of such main trees. And we can also construct the fractal squares with main tree of that configuration, and of that, and also of that, and finally we finish the talk and have a break. Thank you for your attention. And now